people I have worked with. I've worked with many people in my career who basically wants to change the world around him. And he does it by assimilating very well what others say and by a boldness mingled with a great sense of humor and comedy. So I'd like to wish that those many happy years of good health and work and laughter is not here, but hopefully I'll give this to him. Okay, so I wanted to talk about the importance of curiosity-driven research. Just prepared a few slides. I'm standing here to defend basic sciences because the buzz all around is what are your deliverables. Every time I have gone to the government for many reasons, they ask me, what are your deliverables, especially the Atomic Energy Commission. I told them, creation of knowledge, which is a deliverable. Okay, so I just wanted to start with this very famous quote, man's power over nature is the source of history. And I think that man's curiosity about nature is in fact the source of that power. Few people would deny the importance of asking the following questions, like the origin and fate of the universe, the origin and evolution of life on Earth, and how did matter organize itself to think. So these are extraordinary questions actually, which somehow distinguishes us as a species. So basic sciences are therefore involved in the quest to answer these and similar questions. In real brief, the basic sciences are a curiosity-driven exploration of how nature works. And basically my talk is trying to prove my point historically. And let me just begin. We all know that Kepler discovered, this pointer is not working, sorry, but discovered his laws of planetary motion from a desire to make sense of a vast amount of Earth-based astronomical observations of the motion of planets. In some sense, the Newtonian revolution is the foundation of not only physics but also of engineering, etc. And I'd just like to make this point that Kepler is the person who found a symmetry in big data. In modern parlance, what did he really do? He found a symmetry in this incredible astronomical data. So think about it that way. It's interesting. Then another example is James Clerk Maxwell. He discovered the laws of electromagnetism from a quest to make consistent the then laws of electricity and magnetism, and his discovery led to the prediction of light as an electromagnetic wave, and in particular microwaves. It was this prediction that enabled Röntgen, it's a very important point, to interpret X-rays as another form of electromagnetic radiation. And you know that this line of basic sciences over many decades, and that's also very important actually. The gestation period is very long, it leads to electrical engineering, optics, etc. The last example I chose is from biology. It's one of the most important discoveries of the 20th century by Crick and Watson about the information coding scheme of biology from a desire. It was from a desire to interpret the crystal structure of DNA. And their discovery forms the foundation of all modern biology, including gene editing technologies. There's one point I want to make which somehow is a little bit in conflict with some talk we heard this morning. That, from discovery to application, it can be a very, very long time. And we should allow that time. We should not ask for people to produce things within 1 year, 5 years, etc., etc. This is very important point. Of course, it doesn't apply to everybody, but a certain section of the scientific community must do that. Okay, so the history of science basically teaches us that most scientific discoveries are owed to serendipity and curiosity. And they are the ones that drive explorations in what I call this knowledge space. You try to sort of create a space of knowledge, and that often translates into new technologies, which enable new discoveries and so on. And this is a very important point I'd like to make, is that it's not that we have to do basic sciences first and then comes technology, etc., etc. It's very important to realize the importance of engineering and technology for the discovery of the new laws of nature. After all, Galileo used the telescope that was available to him, and so did as I mentioned before, Hubble, when he made this most incredible discovery about the expansion of the universe. He was aided by top quality instrumentation at Caltech. Okay? So it goes all hand in hand. There is no real this first and this afterwards. I just wanted to make this point that you don't get away the impression that I'm only saying that it's basic sciences and then comes engineering and technology, etc. No, it's not like that. There's a loop here. And okay, so now I'd like to what shall I say, support my argument by a quote from Wadia. After the Second World War in the United States, Wadia set up the National Science Foundation, and this is what he says: basic research leads to new knowledge. It provides scientific capital. It creates the fund from which the practical applications of knowledge must be drawn. One of the peculiarities of basic science is the variety of paths which lead to productive advance. Many of the most important discoveries have come as a result of experiments undertaken with very different purposes in mind. Okay, so I thought it's important in support of what I'm trying to say. And now there is a slide on applied sciences. So applied sciences draw from the basic science knowledge bank. It directly leads to technology that shapes the modern world. These are all obvious things: communications, air transport, medicine, medical engineering, large-scale computing, artificial intelligence. All this is the domain of applied research that delivers the ultimate product. Of course, and this is the point I made before, and I want to emphasize this, that there is a feedback between applied sciences and basic research. Example, the Hubble discovery, the discoveries at CERN. If you have been to the CERN laboratory, it is one of the biggest engineering marvels in the world. Everything we know about science is used to make discoveries in elementary particle physics, which you call fundamental physics. So, and LIGO, for example, the discovery of the gravitational waves, they are all dependent on very cutting-edge technology. So there's a loop over there. Okay, so I think I have some time. I started at 1.
It's only 5 minutes.
Oh, okay, all right. Yeah, we are in the same reference frame. Okay. All right, so I just had a quote from this very beautiful book on the idea of the factory of Bell Labs and what it contributed to science. But perhaps these slides are available to you if you can read them, since I have only 5 minutes. Okay. So it says, maybe one study by William Shockley at the West Street Labs, joined by Leighton, Fisk, Lawrence, and Woolrich, among others, met every Thursday afternoon. The men were interested in a particular branch of physics that would later be called solid-state physics, and it explored properties of solids in terms of what happens on their surfaces as well as deep down in their atomic structure. And this is how the transistor came about from fundamental understanding, and basically the backbone of this was the invention of quantum mechanics. We are celebrating 100 years of quantum mechanics this year. And so this leads to, everything you see around you is different because of these discoveries. Okay, there are some examples I'm giving you actually. So the cell phone, for example, which every one of you has, right? So here is a sort of a plaque at the Cavendish laboratory. I think it says that here in the old Cavendish laboratory, J.K. Thomson discovered the electron, subsequently regarded as the first fundamental particle of physics and the basis of chemical bonding, electronics, and computing. That was in the 19th century, end of the 19th century. Then there is, of course, in 1927, or I think, certainly after 1925, 26 or 27, the Dirac equation. And this is about computing. And you must be wondering why there's Einstein's equations there. It's because in order to have this GPS being very accurate, you have to take into account the fact that your clocks will go faster as you go away from the Earth. This is a prediction of general relativity. So now, neither the electron discovery nor the Dirac equation nor the work of Turing had any applications in mind really. But today we are benefiting from it. So I think it's extremely important to allow this type of research and really encourage it and go beyond this 0.69% of GDP that we are devoting to science and technology. There is this other thing which I thought is a good example is the discovery of NMR, and this is Issa Rabi, who's a professor at Columbia University, and he was reminded of his work when he was being examined himself in an MRI machine, and he saw himself reflected in the surface of the machine and said, "I never thought my work would come to this." He didn't do NMR in order to have a medical application, but then it found a very important medical application, which is so fundamental to medicine, medical technology, and also biology, especially neuroscience. The last example I have is about prime numbers, mathematics. Everybody knows that these are the building blocks of the integers, and there are very beautiful relations amongst the prime numbers. You know that modern cryptography is basically based on the problem of prime factorization, to which people from IIT, Maninda Agarwal and Veeraj Kaya and Srivastava made a very foundational contribution. So I don't think they were doing it to sort of, enable banks to be secure, but a fundamental quest of how to solve this type of problem. Okay. Alright, so I'm more or less at the end of my time, and the last thing I want to tell you is the following: that the 2024 Nobel Prize in Physics was awarded to condensed matter statistical and biophysicist John Hopfield and the computer scientist, cognitive psychologist Jeffrey Hinton. Okay, for their work in the 1980s. They built on earlier work by Warren McCulloch and Walter Pitts. This is the fundamental paper that first talked about how to sort of talk about the mathematical structure of the neural network, perhaps trying to emulate brain research. This is 1943. Then comes the heavier learning ideas from the psychoanalyst. Okay? And after all, and finally it goes to the important contribution of Frank Roosevelt, the perceptron. I invite you to really read about all of these things actually, and its history. And this incredible interdisciplinary breakthrough was enabled by decades of curiosity-driven research in different scientific disciplines that now have come together in ways that are making an increasing impact on science, engineering, and everyday life. So this is just from last year, right? And finally, this is the last slide, almost the last slide. So this is the point this is the takeaway message over here. Why do basic sciences need to be protected? This is the following. I think Bush put it brilliantly. He said the distinction between applied and pure research is not a hard and fast one, obviously. And industrial scientists may tackle specific problems from broad fundamental points of view also. It is important to emphasize that there is a perverse law governing research. Under the pressure for immediate results, and unless deliberate policies are set up by the government to guard against this, applied research invariably dries up pure. The moral is clear. This pure research deserves and requires special protection and especially assured support. And I hope that the government of India actually take a leaf out of this page of Farmer Bush. Okay, I'm more or less done. This is a picture I got of Ashutosh yesterday. So, anyway, happy birthday. Thank you very much for